The next problem is a somewhat tricky conservation of energy problem. We have a spring-loaded dart gun is used to launch an object straight up into the air, and it goes up a max of 24 meters when it's compressed some distance. Let's call it x1. So in our picture, we have the ground, the platform, the spring, it's compressed some distance x1, and the object, we're told, rises into the air 24 meters. We'll call that height 1. The next part says that the same system is used, but this time the spring is only compressed half as far. So maybe that's x2, and we want to know how high does the object go above the release point. If x2 is 1/2 that initial compression distance x1. To solve this, let's set up a statement of conservation of energy. When the spring is compressed, it only has elastic potential energy, and when the ball reaches the top point here, it only has gravitational potential energy. So we could say for launch 1, our initial elastic potential energy is equal to our final gravitational potential energy. And if I were to solve for h1, I'd have 1/2 k x1 squared divided by mg, and that whole thing we're told is equal to 24. Now for launch 2, the setup is the same. The only difference is that for our compression distance, we have 1/2 x1 squared, and that's now equal to mg h2. Distributing that square, I have 1/2 k times 1/4 x1 squared, mg h2. Solving for h2, I'm going to keep that 1/2 and the 1/4 on the left-hand side separately. I have 1/4 times 1/2 k x1 squared over mg. But earlier, we had as h1 that exact expression, 1/2 k x1 squared. And so I could substitute that. And I actually now am in a place to solve this problem because I actually have a value for h1, 24 meters. So plugging in our numbers, we see that h2, the height that the object moves when the spring is compressed only half as far as the first time, is 24 divided by 4, which is 6 meters. The next problem looks like a computational problem, but it's really a conceptual problem. A force of 40 newtons is applied to a box of mass 10 kilograms. We're told information about the coefficient of static friction and the coefficient of kinetic friction. If the box is initially at rest, we want to figure out what is the force of friction acting on it. And the first thing that we need to decide is, does this force cause the box to move? To do that, we can calculate the maximum static friction force, which would be the coefficient of static friction times the normal force. The normal force on this box, because it's just sitting there, is equal to the gravitational force. And so plugging in numbers, we have for static friction 0.5, the mass is 10, and to keep things simple, let's just use g as 10 meters per second squared instead of 9.81. Multiplying this out, we get that the maximum static friction force is 50 newtons. The applied force is 40 newtons, which is less than the maximum static friction force. Therefore, our static friction force is going to be equal to our applied force, because static friction is only what it needs to be to keep the object from moving up until this maximum value, at which point it would move and kinetic friction would take over. That doesn't happen because our applied force is not enough to overcome static friction, Therefore, the static friction force is just going to be equal to the 40 newtons that's applied. In the next problem, we have an object that's attached to a string and is being spun around in a circle. And we're asked about information at the top point. Specifically, what is the magnitude of the tension point at this top point? To answer this question, we'll first need to decide what forces are acting on our object. There's going to be a gravitational force pointing downwards, and the only other force acting on it is a tension force, and that's actually also acting downwards. So if I were to write Newton's second law, I'd have gravitational force minus my tension force on the left-hand side equals m, and for my acceleration I actually have an expression for that. Because this object is moving around in a circle, the acceleration is equal to the centripetal acceleration, v squared over r. And since the centripetal acceleration always points towards the center of the circle, and in this specific case that's acting downwards, or pointing downwards rather, we'll need another minus sign. So all these minus signs can actually be canceled out, and we'll just work with the positives. So now we have mg plus tension force equals m v squared over r. I can rearrange this to solve for tension. And if I were to plug in all of my numbers, 2 kilograms for the mass, 5 meters per second for the speed, 1.5 for the radius, minus 2 times 9.81 meters per second squared, put all that into a calculator, I'd end up with something like 1.58 newtons. Nope, that's not this problem. 13.7 newtons, which if I round it is 14. In this next problem, we have a hockey puck that's spinning around in a circle, is attached to a string, and that string is attached to a mass, and that mass is hanging there stationary. And the question is, what speed does the puck have to move so that way the cylinder remains at rest? To solve this problem, we'll need to apply Newton's second law to both of the objects. For the cylinder, we have a force of gravity pointing down and a tension force pointing upwards. And for the hockey puck, I'm only interested in horizontal forces. So there's a tension force here, and the two tension forces, because they're on the same string and there's no massive pulleys or anything, will be the same for each of the objects. So now that I have my free body diagrams, I can write Newton's second law for each of these. So for the puck, the only force present is tension, and because it's moving in a circle, I can use the centripetal acceleration. For the cylinder, it's at rest, so the tension force minus the force due to gravity on it will be equal to 0. Solving for the tension force in my cylinder equation, I can then use that to plug in for the tension force in my puck equation. Solve for the velocity. Plug in values. And then putting this into a calculator, get 1.58 meters per second.